So in this video, we're going to look at how to solve for the consumer's optimal consumption bundle using calculus-based methods rather than graphical methods. This is going to give us a more precise solution, and also if you take a lot of later classes in economics or even PhD classes, it will allow you to answer much more complicated questions than what you can answer using the graphical-based methods. So let me start just by giving an example. Let's assume that we're trying to maximize Antonio's utility. That is, find the consumption bundle which maximizes his utility. And we will say that his utility function is equal to the square root of the amount of Pepto-Bismol that he consumes, which is represented by B, times the amount of fried Mars bars consumed, represented by the letter F. And we can simplify this or sort of rearrange this and say that this is equal to b raised to the power of 0.5 times f raised to the power of 0.5. And this different way of writing it will just make it a little bit easier to solve the problem. Okay, and let's also assume that the price of Pepto-Bismol is equal to 5, and the price of fried Mars bar is 2, so these are all in dollars, and the person's income, or Antonio's income, is 20. Okay, so how do we solve this problem? Well, there's 3 different ways that we could look at. So the first method utilizes some of the intuition or sort of the relationships that we derived using the graphical-based methods. In particular, we found that the ratio of marginal utilities is equal to the price ratio. Well, the price ratio, that's just data, right? We have the prices, either it's in the market or we're given it in the problem or something like that. So that's just there. The ratio of marginal utilities, if we assume a functional form of the utility function, we can calculate it, right? It's just the partial derivative of utility function with respect to the variable that you're looking at. And so that sort of sets the framework or the starting points of solving the problem. Another method we could use is a substitution method, where we'd use the information about a person's income and the prices to come up with a budget constraint, and then find the relationship, that is using the budget constraint, find the relationship between the amount of good F consumed and the amount of good B consumed. Right? Like if you take a certain amount of good B consumed, that tells you how much good F they could buy if they spend the rest of their income on good F. And so that can be sort of the starting point, and then you could go through and solve or have that relationship, plug that relationship into the utility function, right? So we know what F is in terms of B, we plug that in, now we have an equation that only depends on B. And so that's the starting point of solving the problem. The other method that you could use is you could use the Lagrange Multiplier method. This is just an example of constrained optimization. The consumer is trying to maximize their utility subject to a budget constraint. So it fits that framework perfectly. So let's go over some of these methods. I'm going to start with the substitution method. So as I said, the first step of solving this problem using the substitution method is to use the budget constraint to find the relationship between F and B when the person is spending their entire income. So let's start by writing down the budget constraint. We have that their income, so let's say budget here, their income of $20 is equal to, this would be 5 there, is equal to the price of good B, which is 5, times the amount of good B consumed, which is just represented by the letter B, plus the price of good F, which is 2 in this problem, times the amount of good F consumed, which is just represented with the letter F. Okay. Now we want to find the relationship between F and B, so we want to rearrange this equation to solve for one of the variables. Let's solve for F. If we subtract 5B from both sides and divide by 2, we would get that F is equal to 10 minus 5 halves times B. Okay, so from the budget constraint, we're able to get that F is equal to 10 minus 5 halves times B. Now we can take this and plug it in for F in the utility function. Okay, so let's do that. So now we have that utility is equal to b raised to the power of 0.5 times f raised to the power of 0.5. But we're going to plug in for f because we know that given a certain amount b purchased, the amount of f that they would buy with the remaining income is equal to 10 minus 5 halves b. So now we have the amount of good f consumed as a function of b, or represented by this function of b. Okay, so now we've rewritten this utility function in terms of one variable b. It captures how much of good f they're consuming. That's captured right here. Okay, but we've simplified it in that there's only one variable in this problem, so we can use single variable optimization methods. So now what we can do is we can take the well, let me take a step back. So what we've done here is we've used the budget constraint to turn a constrained optimization problem of two variables into an unconstrained optimization problem with only one variable. Okay. So now we can just take the derivative of utility with respect to b, now that we've got in terms of that one variable, and solve. So let's take the derivative of utility, I should say it's a partial derivative, with respect to b. And to solve this, you'd have to use some of the calculus methods I asked you to review, the product rule and chain rule. So if you haven't reviewed those or reviewed those or are having trouble remembering them, I suggest you do that so you're able to use these methods on examinations. Okay, so this derivative, or the partial derivative, is equal to 0.5 times b to the minus 0.5 times 10 minus 5 halves b raised to the power of 0.5. Okay, and then we're going to subtract from that 0.5 times 5 halves b raised to the power of 0.5. Times, let me just try and clean this up a little bit. Times what was in parentheses, 10 minus 5 halves b, raised to the power of minus 0.5. I'm really out of space here. Here, let's move this whole thing over here. Raised to the power of 0, minus 0.5. Okay, and when we're optimizing, we set the partial derivatives equal to 0, or the derivatives equal to 0. Okay, and then we just have to solve for b here. If we were to multiply both sides by, so multiply by, let's see, 2b to the 0.5 times 10 minus 5 halves b all raised to the 0.5. This is going to simplify. So take this first term, the 2 is going to cancel the 0.5, the b to the 0.5 is going to cancel the minus 0.5, and we're going to be left with 10 minus 5 halves b. So that's just basically, we multiply this by this, that's what we get. And next we're going to multiply that same thing, this, by the second half. And the 2 is going to cancel the 0.5. The 5 halves is going to stay. B to the 0.5 times B to the 0.5 is just B. And then the part in parentheses is going to cancel each other because one of it's raised to 0.5, the other is raised to the minus 0.5. It just cancels. Okay? And then we're going to multiply the right-hand side by the same thing, but it's just multiplied by 0, so it remains 0. And we can simplify this a little more. We have 10 minus 10 halves. B is equal to 0, or B is equal to 2. Okay, so this says that when Antonio is maximizing his utility, he's consuming 2 units of good B. We could then plug it back in. Plug it back into this relationship that we found using the budget constraint, and we could then solve for F. So F is equal to 5. Okay, so that's how you solve this problem using the substitution method. Okay, so now let's solve the same problem using the method that I first mentioned, where we're going to use the fact that the ratio of margin utilities should be equal to the price ratio when the consumer is optimizing. And we got that relationship from the graphical analysis or from the previous video. So let's, we'll write this down here. So we're going to write down that the ratio of margin utilities, so margin utility of, say, B over the marginal utility of F is going to be equal to the price of B, which is 5, over the price of F, which is 2. So to solve this problem, the first thing you have to do is actually calculate these marginal utilities. So marginal utility with respect to, or B, is just the partial derivative of the utility function with respect to B. Okay, so we're going to have the partial derivative of utility function with respect to B over the partial derivative utility function with respect to F. That's just the ratio of margin utilities, and that's equal to 5 over 2. Okay? The partial derivative of utility with respect to B is just 0.5 B to the minus 0.5 times F to the 0.5. And the partial derivative utility function with respect to F is 0.5 times B to the 0.5, F to the minus 0.5. And again, that's just equal to the ratio of prices. Okay, so we can simplify a little bit. We have 0.5 in the numerator multiplied by everything, 0.5 in the denominator multiplied by everything. Those just cancel. So let's just take a step back, and I want to clarify something. So if we have B to the minus 0.5 is just equal to 1 over B to the 0.5, or more generally, B raised to the minus A is just equal to 1 over B raised to the power of A. So this is going to help us simplify the problem. In our problem, we have B to the minus 0.5 over B to the 0.5. That's just equivalent to 1 over B to the 0.5 times 1 over B to the 0.5, which is just equal to 1 over B. Okay, so let's put that in. 1 over B. And F to the 0.5 over F to the minus 0.5 is similarly just equal to F. And again, that's equal to 5 over 2. Okay, so We can then just solve this a little bit further and get that f is equal to 5/2 times b. So what is this telling us? It's telling us that the point along the difference curve where it's exactly tangent to a budget line is a point where you have 5/2 as much f as you do b. So 2.5 times as much f as you do b. Okay? We have not yet finished solving the problem. Okay? The problem here is that it doesn't give us a particular amount of f and b. It could be that b is equal to 1 and f is equal to 2.5. It could be that b is equal to 2 and f is equal to 5. It could be b is equal to 10 and f is equal to 25. Right? Which is going to tell us which of these combinations of f and b that satisfy this relationship are actually the ones that solve our problem? Well, we know that the consumer has a limited budget. As you increase b, you increase f as well, but you can't just increase them an arbitrary amount because eventually it would exceed the amount that this person can afford. So what we're going to actually do is we're going to use the information from the budget constraint to help us solve the problem. So from the budget constraint, we have that 20 is equal to the price of b, which is 5 times the amount of b consumed, which is just represented by b, plus the price of f, which is 2 times the amount of f consumed. Okay. Now we could plug this in here, plug in what we found f is equal to in for f in this equation. So that gives us 20 is equal to 5b plus 2 times 5/2 b. Okay, we're just plugged in for f. And now we have an equation that just depends on one variable b. We can just solve for b. And if you go through the same steps, you would find that b is equal to 2, f is equal to 5. You should get all the same solutions no matter which optimization method you use. Okay, so that's the second method. And the last method you could use is you could try to use the Lagrange multiplier method. So let's go through that quickly. So with the Lagrange multiplier method, you start by writing down the Lagrangian function, where the Lagrangian function is equal to the thing that you're trying to maximize or minimize. So what are we trying to maximize? We're trying to maximize the consumer's utility. So the Lagrangian is equal to the utility function. So it's b to the 0.5, f to the 0.5, plus the Lagrange multiplier lambda times the constraint. Okay, so the constraint is the rearranged constraint that's equal to 0. So if we have their income and we subtract their expenditure, which was 5b minus 2f, that should equal 0. So it's a thing that's equal 0, that should be equal to 0 according to the constraint that we plug in inside the parentheses. And then once we've found the Lagrangian, we take the 3 partial derivatives with respect to the 2 variables we're optimizing over, b and f, and then also with respect to Lagrange multiplier lambda, and set each of those equal to 0. So we're going to get the derivative of the Lagrangian with respect to b, and that's going to be equal to 0.5 b to the minus 0.5 times f to the 0.5 minus 5 lambda is equal to 0. And the second equation, take the partial derivative of Lagrangian with respect to f, and that gives us 0.5 b to the 0.5 f to the minus 0.5 minus 2 lambda is equal to 0. And then the third equation is we take the partial derivative of the Lagrangian with respect to lambda, and that just returns our constraint. 20 minus 5b minus 2f is equal to 0. Okay, so now we have 3 equations, 1, 2, and 3, and 3 unknowns, lambda, f, and b, and we just have to solve these 3 equations for the 3 unknowns. I'm going to skip that part right now because that's somewhat tedious and should be optional. But if you have questions about that, ask about it in class. Okay. See you there.